welcome to the second lesson of topological data analysis. Today's lesson is called Homeomorphisms. And this is a day where I explain to you why, for a topologist, a square is a circle and is also a triangle. Here you can see Euclid asking us, well, why would you say that a square is a circle and why is it also a triangle? So this is a question that I would like you to meditate a bit. Basically, in topology, we are not interested in the way our object is drawn on the plane or in the Euclidean space. We are interested in the intrinsic properties of our object. Okay, and from a data analysis perspective, it allows us to escape from units way of representing things. We will only focus on how the data behaves. And so those are the answers of Henri Poincaré and René Thom. Henri saying that mathematics is the art of giving the same name to different things. And René says, topology is a discipline that allows the passage from local to global. All right. So we will define first today what are homomorphic topological spaces. And doing so, we will create very complicated objects. And in order to study them, we will use the notion of invariance. So I'm very excited because invariance is one of my preferred topics in mathematics. And we will have an introduction to that today. So first, the main notion of today's lesson is homomorphism. So we need two topological spaces, xt and yu, the general definition as we saw yesterday, and a map f between x and y. We say that this map f is a homomorphism if f itself is continuous, if it is a bijection, and if the inverse, f to the minus 1, also is continuous. That's it. If you have such a map f between two topological spaces, then we say that the two topological spaces are homomorphic. So I will give you a very simple example. I am in the Euclidean plane, R2, and I consider two circles, two spheres. A sphere in the plane is a circle. The circle of center 0 and radius 1, and the center of center 0 and radius 2. I have a homomorphism between these topological spaces, namely the map that maps x from the first circle to 2x, which belongs to the second circle. So when I say that it is a homomorphism, I have to check that it is continuous, but this is obvious, that it is bijective, this is also obvious, and its inverse, f to the minus 1, this is x over 2, this is also continuous, right? So I can conclude that f is a homomorphism and the circles are homomorphic. Sorry, I hear some noise. Yeah. All right. There is a little issue here. I want to make sure that being continuous here makes sense for you. Because, as we saw yesterday, to talk about continuity, we have to define topologies. on the circle, on both circles. And as I said, when we will talk about subsets of the Euclidean spaces, the only topologies we'll consider are the subspace topologies. So when I say that this map is continuous, I mean that seen as a map between the subsets of R2 endowed with the subspace topology, this map is continuous. And so why is it really continuous? You have to check that the preimage of every open set of this circle is an open set of this one. So let me give you a lemma that allows to prove that in generality. If you have a restriction of a continuous map, then it is continuous. Because you can see that this map F is the restriction of a larger map between R2 and R2, which is simply the map that maps X to 2X. And we know that this is continuous. So its restriction between the two circles also is continuous. So let me read you this lemma. Consider a map G between two topological spaces such that G is continuous. Then you pick a subset A of the first set and a subset B of the second one, and you endow these subsets with the subspace topology. Then the lemma says that if your map has its image into, oh, sorry, here it is G. If G of A is included in B, then you can consider the restriction, G, which goes from A to B. And the lemma says that this restriction is continuous. Okay, so this is how I can prove that this map is continuous. All right, this was very simple. Another example, I take the same circle of center 0 and radius 1, and I take the square of R2. You can define the square as the set of points of R2 such that the maximal value of the absolute value of their coordinates is equal to 1. And I give you here a map that goes from the circle to the square. Okay, this is defined like that. And it turns out that this map is continuous, that it is bijective, and you can show that its inverse is this map. Okay, and this map is also continuous. So F is a homomorphism, and we deduce that the circle and the square are homomorphic. This is another example that I give you as an exercise. In general, in Rn, you can show that the open ball of center 0 and radius 1 is homomorphic to the whole space Rn. So for instance, this ball in R2 here is homomorphic to the plane. Okay. Do you have any question until now? Thank you. Yeah. How can I solve this exercise? I have to find a homomorphism, of course, between the ball and the plane. So I give you in the exercise, in the notes, I give you the map. You just have to check that it satisfies the 3 axioms. But if you have some courage, you can try to find the map by yourself. Okay. Let me show you an example of non-homomorphic spaces. The interval 0 to pi and the circle. So this is interesting because we have a very famous map between this interval and the circle that I call F, and you map theta to the point in R2, cos theta and sinus theta. So this map is continuous because both trigonometric functions are continuous. And this is elementary trigonometry, you can show that it admits this function as an inverse, where arctan is the arctangent. But this time, this map G is not continuous. And so the map F here is not a homomorphism. Okay? So let me show you why. To show that G is not continuous, I have to find an open set of 0 to pi such that its preimage is not an open set of the circle. And I take this one, 0 pi, where 0 is included and pi is not. The preimage of 0 pi by G is this thing here. And as you can see, this set is not open in the circle because it is not open around the first point here. So if this is not clear for you, why 0 pi is an open set of the interval, this is because we endow the interval with the subspace topology of R. And 0 pi can be seen as, the subspace topology is defined as the topology that contains as open sets, the sets that can be written like an open set of R and the subset we consider. So for instance, 0 pi could be written as minus epsilon open and pi open, and if I take the intersection with 0 pi, I end up with this set, which is open. Okay. So G is not continuous. And now I have a question for you. Did we prove here that the spaces 0 to pi and the circle are not homomorphic?
Sorry, can you repeat?
The question is, did we prove on this page that the interval and the circle are not homomorphic?
Not exactly, because you just showed there is, you had to show there was no function, not that any specific function would be the case.
Exactly. What I proved here is that this natural map is not a homomorphism. But to prove that the two spaces are not homomorphic, you have to show that there is no homomorphisms between them. So this is not enough here. And in general, the question of showing that two spaces are not homomorphic is very complicated because you have to prove. Sorry again. All right, so we were here, and I just told you that proving that two spaces are not homomorphic is a tricky question because you have to show that there exists no homomorphism, while showing that two spaces are homomorphic only necessitates to find one homomorphism, and we're done. Okay. And to solve this problem, I will introduce to you the notion of invariant in a few minutes. So before that, I would like to talk about something. Could you tell me in the chat if you know what is an equivalence relation? So I was here. Yeah, I just asked you, can you tell me in the chat if you know what is an equivalence relation in math? So I see a lot of yes. Nice. All right. Being homomorphic is an equivalence relation between topological spaces. Let me explain what does that mean. From now, if two topological spaces are homomorphic, I will write x equal to y. Okay. As it is, it does not make sense. We should precise what topology we are given at x and y, but to write it more simply, I say x equal to y. Okay. So I have a first property for any topological space x. X is equal to x. This means that x is homomorphic to x, and this is really easy to prove. You take the identity map between x and x. It is continuous, bijective, and its inverse is itself is continuous. So any topological space is homomorphic to itself. We have something else, which is called symmetry. If a topological space X is homomorphic to Y, then Y also is homomorphic to X. And this is because if you have a homomorphism between X and Y, then its inverse is a homomorphism between Y and X. Okay. Third property, if we have three topological spaces X, Y, and Z, such that the first two ones are homomorphic and YZ are 2, then we have that X and Z are homomorphic. This is called transitivity. And this is also very simple to prove. If I have a homomorphism between X and Y and between Y and Z, consider the composition GF. This is a map between X and Z, and you can verify that it is continuous, bijective, and its inverse also is continuous. And the three axioms are the axioms of what we call an equivalence relation. Okay, and this is very interesting because an equivalence relation allows to classify the elements of the relation. So what we can do is to separate topological spaces into classes, into bags, into types, and each type will represent some kind of abstract, some essence of topological space, right? So for instance, the square, we've seen that it is homomorphic to the circle, but you can show that it is also homomorphic to the triangle, to any polygon, and also to continuous shapes like that. So this is the first class, which is called the class of circles. Okay, this is a class of homomorphism equivalence. So we have on the side the circles. We also have the class of intervals. All the spaces that are homomorphic equivalent to intervals. We also have the crosses, for instance. So the class of crosses is different from the class of intervals, because we will show in a few minutes that these two spaces are not homomorphic. So this was for spaces of dimension 1. We also have spaces of higher dimension, for instance, the spheres. The sphere of dimension 2. This is a subset of R3. And it is this class contains all these deformed, twisted, bended spheres. Okay. And so an interesting question will be how to describe the different classes of topological spaces up to homomorphism. Because if you can list, if you can understand what are the different classes, you understood topology, right? Up to homomorphism. Though, as I said, this is a tricky question. If I give you two topological spaces, can you tell me if they are in the same homomorphism class. For instance, these two ones, they are crosses. But in general, this is difficult. And mathematicians invented something really nice that is called invariant. And today, I will give you two examples of invariant, connected components, and dimension. So let's start with connecting components. So we have first to define what is a connected space. Take any topological space, X, T. I say that X, this topological space, is connected if the following property is true. If I take two open sets, O and O prime of X, such that they do not intersect, they have a trivial intersection, and such that they cover the whole space, then we must have that one of them is the empty set. You can rephrase this definition like that. If a space is connected, then you cannot subdivide it into two open sets that are non-empty and disjoint. If you want to divide your space in two open sets, disjoint and non-empty, this is impossible. So for instance, this here is a connected space. Okay. This one on the right though is not, because if I take this open set O and this open set O prime, then they are disjoint, open, and they cover the whole set. So this is not connected. Let me give you a proposition. In Rn, the balls are connected. Okay, this is a really visual notion, right? Connectedness. And more generally, any convex set is connected. Okay. Now we have connectedness. We can talk about connected components. Let's take any topological space X and take a point, little x, in large X. I can define the connected component of X. The connected component of X is defined as the largest subset of my topological space that is connected. So for instance, the connected component of X here would be this set. Okay, it is connected, and it is the largest one we can find. If I were to add points in these other components, it would not be connected anymore. The connected component of this point here is this ball, right? Same. Connected component of X here is this ball, and the connected component of this line, of this point here on the line is the whole line. Okay. And what happens is that you can subdivide your topological space into connected components. So you can consider the different connected components, and this forms a partition of X. So for instance, here, X is a space that admits 4 connected components. So let me give you a precise definition. Here, I'll define what is a set. Yeah.
Each partition of this set must be an open subset.
Yeah, because you can show that a connected component is open. This is a lemma, a statement. And moreover, if you have a finite number of connected components, you can also show that they are closed. So for instance, here in this space X, we have 4 connected components, and they are all open and closed, according to the subspace topology we put on this. Is it clear?
I'm not sure.
No? Rephrase your question, if you can.
Each part of each circle and each part, I didn't understand why they must be open subset, or it's the definition of the topology.
Yeah. Let me give you an example. Here I am in the plane, and I consider a ball, all right, that I call X. And then I consider the subspace topology on X. Do you agree that this is an open set?
Rafael, I think we cannot see your screen. At least I can't.
Oh, all right.
I just see the slide.
It's the camera.
Oh, okay. I will move my. Can you see me right now?
I do.
Yeah. All right. So I will move my hands. I take a ball in the plane. All right. I take any ball. And then I consider the topological space, which set is the ball, and which topology is the subspace topology. So this will be.
But the frontier of the ball is inside the set or not included in the set?
Yeah, I will take the boundary. I will take the frontier. So I'll take a ball, a closed ball, a ball with its boundary. So a ball with its boundary is not an open set in the plane, right?
Yeah.
But if I consider the topological space that consists in this ball endowed with a subspace topology, then the whole set is open.
Okay.
This really is a matter of definition, because remember the first axiom of a topological space: the empty set must be open, and the whole set must be open. So in particular, in the subspace topology, the whole set is open also.
Okay, I understand.
All right.
It came from the definition we saw yesterday.
Sorry?
This came from the definition of topology we saw yesterday.
Yeah. I will rephrase this once more. This ball seen in the plane. So say that we have the boundary. This ball seen in the plane is not open, but seen in itself, seen in the subspace, in the topological space endowed with the subspace topology, it is open.
Okay, thank you.
Yeah, so we can show that a connected component is open in our topological space, and if we have finitely many components, then are also closed. Well, we can define the number of connected components like that. Take a topological space and suppose that you can cover your space with n open sets that are non-empty, disjoint, and connected. Then they are, then we say by definition that the space X admits n connected component. I do not even ask for the sets to be open here, because as they are connected, they have to be open. This is the lemma. Okay. I hope this is clear. Let's go to the third part. I want to show you now what does it mean for the connectedness to be an invariant. This is the most important proposition. If I have two homomorphic topological spaces, then they must admit the same number of connected components. So, for instance, I am not homomorphic to the union of two bottles, because the union of two bottles has two connected components, and I am connected. I have only one connected component. Another example that I give here, the subset 0,1 of R is not homomorphic to the union of 0,1 and 2,3 in R. Okay, because they do not admit the same number of connected components. So let me give you a proof of this fact. We take two topological spaces, X and Y, and we suppose that they are homomorphic. I want to show that they admit the same number of connected components. I denote n the number of components of Y and m the number of X. So as Y admits n connected components, I can use the definition I gave you earlier. It means that I can find n sets, OI, such that they cover Y, and such that they are disjoint, and non-empty, and connected. And I'll tell you, without a proof, but you can do it easily, that they are open. So in order to prove that X have that many connected components, we will pull back the component of Y on X. So define for every OI its preimage, OI prime. What we have is that each of them are open. We also have that the OI prime covers X, because I say here because F is a map. This is very trivial statement. If you take the preimage of the image, you obtain the domain of the map. Moreover, these preimages are disjoint. Okay, you can write this set theoretic statement. And also, we have that every preimage is non-empty. It is non-empty because F is a homomorphism, hence it is a bijection, hence any point in the codomain has a preimage. Okay, so what I did not prove here is that the sets O prime are connected. And because I only have that X can be covered by n disjoint, non-empty open sets. I do not say that they are connected. And you can show that if a space can be covered by n disjoint non-empty open sets, it admits at least n connected components. So here we have that n is lower than n. But since F is a homomorphism, we can do the same argument in the other direction. I just take the same proof and I replace y by x and n by m, and I obtain that at the end, y admits at least the same number of connected components than x. So, and we have these two inequalities. This means that they admit the same number of connected components. All right. So this gives a tool to show that spaces are not homomorphic. And this is the very essence of an invariant. If I want to show that two spaces are not homomorphic, I will find an invariant, here the number of connected components, such that my two spaces does not have the same value, the same invariant. So I gave you this very example of one topological space having one connected component and one having two. We can go a bit further. We can prove now that the circle and the interval are not homomorphic, as I told you in the beginning. We have to work a little bit. To prove that they are not homomorphic, we will reason by contradiction. Suppose that they are. So we have a homomorphism between the interval and the circle. There is no contradiction at the moment because the two of them have one connected component. But what I will do, I will remove a point from the interval. Okay, x, any point of the interval. I look at its image on the circle, and I also remove this point of the circle. So my homomorphism, F, restricts as a homomorphism between the interval without the point and the circle without its image. Okay, so I have a homomorphism between the interval without a point and the circle without a point, but the interval without a point, it has two connected components, right? It is homomorphic to the union of two intervals. It is actually the union of two intervals. But the circle, if you remove a point, this is still connected. This is an interval. So this is a contradiction because we cannot have a homomorphism between spaces that admits a different number of connecting components. I have a question of Kevin. The number of connected components is always finite. It is not. For instance, consider Z, the subset of R, the set of integers. Each point is its own connected component. So we have an infinite number of connected components. All right. Do you have any question? I'd like to propose a mental exercise. Can you prove that the interval and the cross are not homomorphic. So this is the interval.
Can you please repeat
The question?
The interval and what?
The cross. The cross.
Ah, okay. Thank you.
Yeah, Guillermo. Yeah.
If you remove the cross point, we get the four subsets. And
yeah. Same proof. You suppose that you have a homomorphism between the circle, the interval, and the cross. You remove a point, the center of the cross. This has an image. You obtain an interval without a point. So this is two connected components. And the cross without the center point is four connected components. So this is a contradiction. Thank you. So you see now why the class of intervals is not the same as the class of crosses. You can prove a lot of statements like that with the same reasoning.
Raphael.
Yeah.
Can you just go back to the last slide? It's a question.
This one?
Yeah. No, for the crosses. Sorry, the class of crosses. Yes. This number of intersections is invariant? Or is just an example of the images?
Can you repeat?
The number of intersections of the lines, it's invariant, right?
Yeah, so this is not easy to define, but you could try to define the number of branches at a point, and this will be also an invariant.
Okay, and because if there is no, we have a problem with the bijection, doesn't it?
Yeah, for instance, if I would consider, how can I do that? A space that has three branches, like my arm and two bottles, you have three branches. You can show that this is not homomorphic to a cross like that.
Okay.
Because you will prove that if you had a homomorphism, then the center should be sent to the center of the cross and of the tree thing. And then you remove these points and you obtain three connected components and four connected components. So it's not much.
Okay, thank you.
Oh yeah, can I draw? If you go to view option, annotate. Draw. Oh, awesome. Oh, I can do a drawing. For instance.
Yes, it's not the best choice, but you're trying to draw something in your notebook. So if you draw it on the screen, I think it might be better. Yeah,
maybe better. Let me try to prove something. I want to prove that the interval and the sphere are not homomorphic. This is a sphere in the space.
Do you guys see anything? I can't see any drawing.
Oh.
Me neither.
Mm.
It's not showing here.
And what about
Yeah,
that?
now it is. Now it is.
All right. Can you see an interval and a sphere here?
Yeah.
Yes.
Okay. I will use the same reasoning to prove that the interval and the sphere are not homomorphic. I suppose that they are. I remove a point on my interval. Here. Oh, please be read. Yeah. I remove a point here. This has an image here. And I obtain here a topological space that has two connected components, and here a topological space that has only one. The sphere without a point has only one connected component. Now, say that I want to prove that the circle is not homomorphic to the sphere. I will do the same. This is a circle. This is a two-dimensional sphere. I suppose that they are homomorphic. I remove a point of the circle. It has an image here. But I'm stuck. I'm stuck here because the circle without a point is has one connected component, and the sphere without a point also has one connected component. So this not work.
Maybe if you remove another point.
Yeah, I can do that. You can actually remove 2 points. Up. And I obtain a topological space that has two connected components, and here only one. So yeah, this works. Let me find an example where this does not work. Let me try something. If I,
Rafael, I'm sorry, can I just ask a question?
of course.
I just want to be clear in the method that you're using to prove. You're using that result that you just proved about the topologies, the restrictions are still the homomorphism is still valid for the restrictions, right?
Yeah,
that's
this
the
is
result
important.
you're using. Okay.
Exactly. Yeah, this is very important. Yeah. All right, say that I would like to prove that the sphere and the torus are not homomorphic. Do you have an idea of how we could do that? Guilherme says, take a whole slice. Yeah, let me show you. Instead of removing a point, we will remove a circle on the torus. So this circle will become a circle also somewhere on the sphere. But now, the sphere without a circle has two pieces. It has two connected components. And the torus without a circle is a tube, a cylinder. It is still connected, still has one connected component. Lucas?
The sphere and torus is a solid sphere or only the shell?
No, when I talk about torus, it's only the boundary. It's the surface, not the inside. Does it make sense that if I remove a circle from the torus, this is a cylinder? Okay.
Yeah.
Cool. And I see a question of Lucas. We define connected topological spaces, but not connected sets. Is it the same idea? When I say connected sets, I mean connected topological space. I don't know what is a connected set. I need to have a topology on it. Okay. So actually, I cannot think of an example where this method does not work. This is really powerful. Still, I have another invariant that I would like to introduce to you today. It is called dimension. Up. All right. So this story begins with a very important result, which is called the invariance of domain. And it goes like that. If you take two Euclidean spaces, Rm and Rn, such that M is not equal to N, then they are not homomorphic. For instance, R0, the point, is not homomorphic to R1, the real line. And this is not homomorphic to the plane, and so on. This result, we cannot prove this today.
Can you prove this using cardinality?
Sorry?
Can you prove this using the cardinality, using an argument about cardinality of the sets? Not really, right?
And no, you can't, because there exists, yeah, I mean, except this one, there exist bijections between all these spaces. For instance, do you know the contour curve? You have a bijection between the line and the plane.
Oh, you do?
Yeah. How is it called? I don't remember the name of it, but I will look for it just after the lesson. But it's kind of a fractal, and what happens is that this is not a homomorphism. Oh yeah. Thiago says, show that R2 and R2 without 0 are not homomorphic. Yeah, for instance, can you prove that R2 and R3 are not homomorphic? Yeah, this is as the sphere and the torus. But if you want to prove that in general, for instance, the space of dimension 4, R4 and R5 are not homomorphic, this is really difficult. So let us accept this statement at the moment, and we'll prove it next week. So yeah, R and R2 are not homomorphic. This is the same example as I did many times before. So you just remove a point from the line and a point from the plane, and you obtain two connected components and one connected component. I precise here that we can use this reasoning to show that R and Rn are not homomorphic for any n greater than 1. But this is all we can do. Maybe R2 will a little work. But thanks to this theorem, invariance of domain, I can define something very interesting, which is called dimension. Consider a topological space. I say that this topological space has dimension n if for every point of my space, I can find an open set around this point, such that this open set is homomorphic to Rn. This is a definition of dimension. For instance, the circle has dimension 1 because if I take any point, I can consider an arc. This is an open set around my point, and this arc I can find easily a homomorphism between the arc and the real line. You can just find a homomorphism between the arc and a finite interval, and then we know that the finite interval is homomorphic to the whole line. All right, another example, the sphere has dimension 2, because if I take a point, I can consider this cut here, this small ball, this disk, and I can find a homomorphism with a disk in R2. Okay, this is true for any point that I will choose on the sphere. So the main understanding, the main interpretation of this notion of dimension is the following. A topological space has dimension n if locally around each point it looks like the Euclidean space of dimension n. If locally it is homomorphic to Rn. All right, and we are lucky because dimension is an invariant. If we have two topological spaces that are homomorphic, then if one of them has a dimension n, the other one also has dimension n. So dimension is an invariant. I should add something here. All topological spaces does not have a dimension. For instance, if you take, what could you take? If I consider a ball here with a branch, this is the branch has dimension 1 and the ball, the disk, has dimension 2. So you cannot define globally the dimension of this space. So this thing does not have a dimension. All topological spaces does not have a dimension. But if they do, if two homomorphic topological spaces have a dimension, then the dimension must be the same. All right.
Can you explain again why not all topological spaces have dimensions?
Because I say that a topological space has dimension n if each point admits a neighborhood, if around each point you can find an open set that is homomorphic to Rn. But in my example, where you have a disk and a branch, around each point in the disk, you have an open set which is homomorphic to R2, and in the branch to R1, R to the 1.
All right, thank you. That's clear.
And this is not the same exponent.
Yes, but the open circle has dimension 2, isn't it?
The open circle. What is the open circle?
It's when you don't have the border. All the points. For example, if you take center 0, the disk with radius 1 is all the points that the distance to 0 is less than 1. Doesn't take the border, you know.
Exactly. Yeah.
This one has dimension 2.
The open ball in R2, the disk has dimension 2. Right. Yeah. Exactly. And all right, we have a proof here of this statement. Let me read the proof because it's interesting. It's very easy, but you will understand better. Suppose that we have a topological space X of dimension n and another topological space Y, which is homomorphic to it. The homomorphism being G. I want to show that Y also has dimension n. So I take any point in Y, little y, and I consider its image by G, X. We know that X, the set, has dimension n, so we can find an open set which is homomorphic to Rn. Okay, now consider the pre-image of this open set by G. We have an open set of Y, and our point little y belongs to this pre-image. So I can consider this composition, H and G, and circle G. This is a map from an open set O prime to Rn, which is an homomorphism. So locally around Y, it looks like Rn, and this is true for every Y, so Y has dimension n globally. Okay, this is it. I see a question in the chat. What is the dimension of a cross? And yeah, you're right, Bruna and Lucas. The cross does not have a dimension. We would like to say that the cross has dimension 1, but take the center point. You cannot find an open set around the center point that is homomorphic to R. It doesn't have a dimension. Well, this is the end of the lesson. So I introduced today the homomorphic equivalence point of view we will adopt as topologists on topological spaces and on data. And in order to study these classes of homotopy equivalence, homomorphic equivalence, I introduced two invariants: number of connected components and dimension. These are very basic invariants. Next week, we will study one of the most important invariants of topological spaces in mathematics, and it is called homology. And this is the whole point of this course, because persistent homology in topological data analysis is something that will help us to estimate homology. And yeah, so these are the exercises for tomorrow. And thank you very much for today.